We call phi the deformation mapping and f the deformation tensor. This expression x as the function of p and p of x comma t is not just deformation. What is it called? I may not have mentioned it, but this expression is a word. The word is common, motion. It describes the change in position or material coordinate and with respect to time. Okay, so we saw what is velocity. Velocity in material frame of reference. So that velocity v with a tilde sign of x comma t is the derivative of spatial position with respect to time at a given material coordinate. When you write it, please use nice large font to make sure I understand what you're writing. If your lowercase and uppercase look pretty much the same, I'll be super confused. Okay. So you have your material velocity as the derivative of position and acceleration a tilde of x comma t is the second derivative of position with respect to time at a given material for a given material particle. From here, you can eliminate x using the motion x equal to p of x comma t, which will give you v in spatial coordinates. X comma t is v tilde of x, which itself is a position of function of x comma t spatial and time. So this is your cheat sheet basically, like a version of your cheat sheet. And last lecture I mentioned I'm going to allow any books or notes, but no electronic devices for the second exam. And similarly for acceleration of x comma t, that can be material acceleration of x comma t and t. So this is basically the course so far, or sorry, this unit so far. Of course, I summarize. There is a little more details, but I'm sure you're aware of it. Broad takeaway, these are all measures of, we can say, local deformation. Now we are going to see measures of the rate of local deformation. From a static world where only length changes or change in something is being the interest so far, we are now going to see measures of the rate or rates of local deformation. Okay, that's our big leap. Now, can I erase? Yeah, sure. So, for the sake of completeness, I'm also going to write this. We get material velocity, that's easy. And you can use the motion to get the spatial velocity just by substitution. You can get the spatial acceleration using the same approach, or you can also write a of x comma t is partial derivative of the spatial velocity with respect to time plus the deformation or a strain rate tensor dot velocity. This is from the idea of material derivative, which we went through last lecture, where L is a spatial tensor, which is the derivative of V with respect to X. So you can write this is partial Vi over partial Xj, Ei, Ej. So there are two quantities that kind of are pervasive in the study of continuum mechanics. One being the deformation tensor, which is very extensively used in describing strains or solid mechanics situations. And then the other is strain rate tensor, which is ubiquitously used in fluid mechanics whenever there is a deformation. It is not the actual deformation, it's the rate of deformation that is measured. So you can write hint fluid mechanic or fluid behavior, hint solid behavior. And of course, reality is in between. We talked about geology and time scales and everything. Okay. All right. Can I erase the left side? Section 3.6.2. 3.6.2. We are going to see rate of change of local deformation measures. Rate of change. What's happening? Change of local deformation measures. What's the most basic local deformation measure that we saw previously? We wrote dx is equal to f dot dx, right? In index notation, this is dxi equal to fij dxj. Right? What we are going to do essentially is we are going to take the vector dx and ask what is the time rate of change of dx, which is denoted by the symbol dx. If I write this bar with a dot, that is a shorthand for time derivative. Okay, so the bar and dot denotes derivative with respect to time. And we do know that what is dx? Dx is dxi ei cap. That's how we write it as a vector in the spatial coordinate system. So if we are interested in the rate of change of with respect to time of this vector, that is like writing dxi ei dot, and from the beginning we have been saying that these basis vectors are non-rotating, they are not changing in time, so they don't really have any time dependence on by themselves. So we can say this is dxi dot times ei. And what is dxi? At least we know that through the deformation tensor, that would be Fij dxj dot ei cap. This I can write Fij dot dxj ei, because dxj is the strain or the change in length or the length of an infinitesimal element. There is, think of it this way, you are applying or you are taking an element in the referential coordinate, you are subjecting it to a deformation or subjecting it to a motion. Motion is just a generalization of a deformation, which includes time difference. So you are subjecting an element to a motion and then asking the question in the spatial description, what is the rate at which the position will change? If I subject it to a motion, which is basically deformation plus some translation or some rotation. So in that case, we have come to the point where we write dxi dot is fij dot times dxj ei cap. We need the derivative of the deformation tensor, or we need the derivative of the components of the deformation tensor. Are you with me so far? The thread is okay? Martiza, you're okay? All right, let's think about f. What is fij? Partial xi over partial xj, right? So if I want fij dot, that would be partial xi over partial xj dot. I'm basically saying time derivative of that. So this is like writing derivative of xi over xj, which is derivative of xj with respect to xj and xi over time. Can I do this? Can I swap the order of differentiation? I can, because if I know my xi is phi of x comma t, it's like saying if I take the first derivative of phi with respect to x and then time, I'm sorry, with respect to xj and time, this is same as the second derivative with respect to time and xj. Okay, so this is allowed, which means this is partial over xj, and this quantity is, what is this quantity? Okay. What is that quantity which we just saw at the start of the class? What is the derivative of the spatial coordinate with time at given or fixed material coordinate? Partial x over partial t at a given x is what? Just did the quiz. This is material velocity. We just did the quiz. You came up and wrote. Right? So this quantity in here is the material coordinate or the material velocity component of material velocity. So this is partial over partial xj bi over xj. What is it? Unit which you can write partial over partial vi over xj or bi over xj multiplied by xi. So this is partial of vi over xi multiplied by xi over xj. Wait, keep missing it. This quantity here is Lij multiplied by this is Fjj. So you have Fij dot is equal to Lij multiplied by Fij material, which is like writing the deformation tensor dot is L dot F. As I go further, I hope you will appreciate how important is F and L, because if you know the two of them, you can work out any other measure of deformation or deformation rate using the subsequent formulas. That is why your homework is more focused on calculating properties based on F. Okay. So this is an important relation. The rate of change of deformation or the rate of change of the rate of deformation tensor is equal to the velocity gradient or the strain rate tensor. So I'll give the names here. F is the deformation tensor. L is the velocity gradient. See, if you understand everything perfectly, we don't need to repeat this, or we don't need to say, is this a mixed order tensor, or if this is a spatial tensor, or this F dot, F dot is the rate of deformation tensor, and would it be spatial, mixed, or material? Would be material. I'm sorry, it would be mixed because I already wrote it here. It's right here will be also mixed. If we all understood everything perfectly, we don't need to keep repeating this, but bear with me. If there are like 10 or 15 people, different people will understand or it will click in your head at different times. So you might be like getting it for the 8th time, you might be getting it in the 10th time, you might be getting it the second time, but I have to say it 15 times. So that statistically it will reach everyone. So I might look like an idiot for saying this over and over and over, but that's the job. All right, so we are back here. We wrote Fij. You can replace Fij dot with Lij, Fij, Dxj. That would be Dxi dot. What is Fij Dxj? Dxi. So this is Lij Dxi. So Dxi dot is simply Lij multiplied by Dxi. That's why Lij is going to play a bigger role whenever we talk about local rate of change. It's just related to the local velocity. Local velocity gradient, I mean. So this is dxi, the rate of change of position along direction 1, 2, or 3. But usually, what is the quantity that we care about? I mean, can I erase this? Are you done taking pictures? All right. I'm going to erase this. I'm going to erase this and write. Start with ds squared. This is dxi, shorthand for dx1 squared plus dx2 squared plus dx3 squared. Okay. I want to calculate what is the rate of change of ds squared or ds squared dot. That would be dxi dot. So if you have, let's say, for example, x squared, and you write x squared dot, what is this? Yeah, this is shorthand for derivative with respect to time of x squared, which you can write 2x multiplied by dxv, or this is 2x x dot. Or in other words, if you have some f of x dot, this is f dash of x dxv, or f dash of x times x dot. Okay, so this is 2 times dxi times dxi dot. Okay, you would agree? Just a symbol. Okay, what is dxi dot? We know that this is 2 times dxi multiplied by lij dxi. So this is 2 times lij dxi dxi and you have Lij, of course. Okay. Actually, we should write this dxi Lij dxj. So this would be dxi dxj. Do you understand why this should be Lij dxj? Anyone? Can you tell? Removing what? To sum over j, you're saying. Yes, that is when you already used that symbol I here. So when you write dxi, it has to involve summation over another dummy index which is not used here. So you need to introduce j here. Okay. So this is 2 times Lij dxi dxj. Okay. So an observation to make here is dxi dxj is a symmetric term or product. That is, if you swap I and j, their total does not change or sum does not change. Okay. So you can take L. What do we know about any tensor? It can be represented as the sum of a symmetric part and an anti-symmetric part. Any tensor can be split up that way. If you have dxi dxj, which is symmetric, if you multiply that with another anti-symmetric component, that will all add up to 0. Because anti-symmetric by definition looks like this: 0, 0, 0, a minus a, b or minus b, b, c minus c. This is how an anti-symmetric component looks like. If you multiply this with a symmetric component, that part will not contribute anything. So the reasoning is Lij can be split as a symmetric part plus, I'll use some symbol like d dash ij. So this is the symmetric part and this is the anti-symmetric part. We can forget the anti-symmetric part because it won't contribute anything. So we can write dij is half Lij plus Lji and dij dashed, which we don't need anyway, is half Lij minus Lji. So 2 times Lij, 2 times Lij can be written as dij plus dji dash dxi dxj, and this is simply equal to dij dxi dxj, and the other just goes away. Actually, I still keep including d. Yeah. So d, which is defined as L plus L transpose divided by 2, is called Huh. Funny. It's called the, are you ready for this? The rate of deformation tensor. I will register my surprise and disapproval of this name because if F is the deformation tensor, its derivative is what should be called as rate of deformation tensor. But this is a legacy. This is a matter of legacy because even before continuum mechanics came into existence or this tensor framework came into existence, fluid mechanics people have already thought of this expression. And they called it rate of deformation tensor. Not super hung up on names. What I would say is, where does L come from? The velocity gradient. Velocity gradient is right here. L is partial V over partial X. If you can understand that thread and the thread that L can be expressed as the sum of a symmetric and antisymmetric parts, we are relating the change in rate of change of length. So this is rate of change of length elements of an element, and we are relating that to that of the tensor Dij. You get this threading right, I don't care for names so much. Okay, so I won't ever ask a question in the exam that says, here is the motion, calculate the rate of deformation tensor. Expecting you to know the name is not my point. If I want you to calculate something, I'll give that quantity and say how that quantity is defined and then ask you to compute. So I would say calculate D, the symmetric part of the velocity gradient L defined as L equals, that's it. This question doesn't require you to remember nothing except differentiation. Okay. So the rate of change of length of an element is related to the symmetric part and also the antisymmetric part, for which the book gives this symbol W, Wij. Wij. If Wij doesn't contribute anything to the length change of the element, is Wij totally irrelevant? No. If something, if a deformation doesn't contribute to change in length, what else can it contribute to? Sorry? Can you elaborate? So if you are here, you move here, that is change in position. You are contributing to deformation. So maybe you are looking for a different word, not position, but some other word which is, can I say angular position? What is the word for angular position? I am here. At 1 o'clock, I see you. At 10 o'clock, I see you. What is the word we use to denote your position relative to me and your position relative to me? Rotation. Think a little further. Orientation. Right? So if a deformation doesn't contribute to change in the length, it can still contribute to change in orientation. That is what we call angular position. Right? So when you think of torsion, what did we see previously? Torsion is a sum of rotation plus bending, or rotation plus bending plus stretching. If you take away the parts where you are inducing change in length or stretch along different directions, then you are left with pure change in orientation or pure rotation. So this antisymmetric part W, which you can write W is L minus L transpose divided by 2. In fluid mechanics, this tensor is called the spin tensor, as in something is spinning tensor. Okay, we are seeing a long list of these quantities, right? Uh, can you think of a situation where you would actually use these, and what would be the utility of defining a deformation or a spin tensor and so on? Can you think of a way that these will actually be useful?
Demolition of a building.
Why?
I know they have to figure out which parts are like structural. So
Okay, so we in this class at least we are not thinking in scales of multi-systems. We are thinking of a material which is homogeneous and something that is small so that you can do a measurement or a deformation experiment or some kind of loading. When you think of a building is a multi-component structure. There are walls, pillars, beams. There is a lot of empty space. So that's not what we are going for. If you are, for example, measuring the velocity field in a fluid flow, if you take a technique like uh, how many of are all of you aware of the word particle image velocimetry, PIV? Heard of it? Okay, no one. Okay, so when you look at let's say for example you are flying a drone and your drone is stationary for a moment and you are taking a picture of a river that is flowing beneath and that river has a flow velocity. So maybe you can make a time lapse video of the river flowing below you. Okay. Um, if you can take two shots, two frames at the same position in successive times, the fluid parcels would have shifted slightly. So you can calculate a delta R for each little fluid parcel, and from the delta R you can calculate the velocity, delta R divided by time between your two photographs. This is the core of PIV. It's essentially to visualize an entire fluid flow. So if you have a field of view that is like a rectangle, you can get the velocity at every point in that frame. Okay. Using such a method, suppose you are able to measure the velocity field of a fluid over time. Okay. Now you can, the velocity field is velocity at every position, comma time at a given time. It's just a lot of data. Do you see that? If you have a river, if you have a rectangular field of view, it's just at every point you will get two vectors, a x component, a y component, and a time. What are you going to do with just a bunch of such xy components and time? How do you turn that data into quick understanding? What quantities can you compute that will allow you to quickly understand whether this river is just flowing or is there some kind of a vortex in the middle that is causing the river water to spin? How do you understand such, how do you derive such physical insights? So for example, if the river is just gently flowing, you can compute this quantity vorticity and you'll find out that the vorticity will come out to be 0, which means if you drop a leaf in the river, that leaf will just travel along the streamline to the end of the river. If the river had a non-zero vorticity, if you put a leaf here, it will undergo a swirl and it will keep on not only moving forward, but also swirling forward. So that river has both transport or the rate of deformation as well as spinning. Suppose you put a river at you put a leaf at a point, you never see it going there. All it does is circle in the same zone. It means that river has only vorticity and no deformation. So these quantities, whether they are zero, says something. If they are non-zero, that says something. So they are all designed and developed to derive insights from data. That making sense to you? It's easy to get position or velocity in spatial or material frame. There are enough ways to measure those. Okay, you can generate lots of data. How do you derive some meaning from the data? You compute these quantities, and each quantity has a physical interpretation. What I'm saying now applies for all the quantities that we have seen. Okay, so I don't want you to just see these as some rote formulas and you forget about it the next minute I ask you. It's not that every formula gets you some meaning out of it. And that's what the examples are supposed to help you find out. Okay, examples and homework problems. All right. So first we saw the rate of change. We saw what is dxi dot. Then we saw what is ds squared dot. Two things we have seen today. Okay. Then we want to calculate what is ds dot. ds is the change in length. ds squared is the squared of that quantity. And why is ds itself important? Recall the stretch is ds divided by ds in material frame. It's not the squared that ultimately determines this, it's the value ds. Okay. So you can start here. I'm going to give you 2-3 minutes and see how far you can get through in deriving ds is equal to dxi square root. So ds dot is square root of dxi dot. What would come next? What would come next? Louder, please. 1 by root of dxi. 1 by square root of 2 times dxi, and then you have to write dxi dot. We know at least what is dxi dot, right? So this is 1 by square root of dxi. Make sure I write it right. Is equal to dij dxj divided by square root of dxi dxi. Wait, no, wait. start from here. dxi dxi. So this is square root of ds squared. So I'm going to substitute for ds squared, okay, which is anu. You're right. We'll start here. 1 over square root of 2 times dxi dxi multiplied by dxi dot. And dxi dot we'll write is 2 times lij dxj. dxi dot is lij times dx, not 2 times. Okay. So coming back to ds dot, that is 1 over 2 times square root of, we'll just write this 1 over ds multiplied by, sorry, 1 over 2 times square root of dxi multiplied by lij dxj. I'm going to do something which is divide both sides by ds. So the book here skips one step. They write this, okay, and then they say next step is this equal to dij dxi dxj divided by ds. They just directly write this here. I would like to understand why or how. Forget all this. The book does this leap. You can look at it. One step they have this, next step they have this. Let's try to reason that. That will teach us something. Okay. So actually they have this expression and then they jump over to this. So can we understand the thread of reasoning here? Like prove this equal to that. Any thoughts? How do we go from here to there? No, I'm asking to understand. You have dxi square root and then derivative. Nominally, what you would do is you will write this 1 over square root of dxi, and then you will write dxi dot. And dxi dot is known as dxi dot is equal to lij times dxj. Lij times dxj. Let's say you substitute that. So this gives you 1 over square root of 2 times square root of dxi, and then you have lij dxj. No contradiction so far to me. I hope the same with you. From here, how do you end up with this? That is the question. After teaching this a couple of times, what I understood is if we start accepting what this book says, as if you do this, obviously you get this. It's a straightforward manipulation. Guess what? It's most often not straightforward. You have to actually sit and try to find out the pieces. There will be something you will learn each time. Like the other day, we learned about transpose and inverse, the dyad switching and the index switching. So I feel that if we reason out how from here to here that is possible, we'll learn something. So to turn this is ds. We have a ds here. We have lij dxj. So still something is missing. I would like you to think about this. Okay, it's easy for us to skip this and just keep going forward, but I want to see how well you can actually put these or interpret these steps. Okay, I'm not giving this because yes.
See, earlier in the notes, we read ds squared equals dx.
Yeah,
I dxi.
yeah, that's where we started. Yep.
Can we sub that into the bottom of this here?
So you want to call this ds.
ds squared.
Okay, so we'll start here 1 over 2 times ds lij dxj. That's still that. Then okay, I agree with so far. How do you go from here to here?
No, we at least have ds on that side of the equation now.
Say it again.
I said we at least have ds on
Yeah, we have the denominator. How is this same as this?
Okay, there, yeah. You just need to prove that Lij equals Eij dxi.
That or some reasoning to why. So here you have only xj. So if you leave this, the quantity still has index I. Over here, if you have dij, dxi, dxj, that has no free indices left. See, this is only to relate it with dxi dot. So this still has a index I left. Whereas this has no index left. This is a scalar, and so is this. So we are not. I mean, it's not like you can directly go from here to here. All right. So yeah. What are we missing here in this step? I see something. How about if I write this is 1 over square root of dxi multiplied by dxi dot. Because what is our identity? F dash of x times x dot. If your x in question is dxi, shouldn't you do the derivative of dxi, which would be 1 over 2 times square root of dxi multiplied by, what is this? 2 times dxi dot. Do you agree with me so far? And see. So this is the 2 goes away, 1 over ds. So far so good. Multiplied by dxi, and then I have dxi dot, which I'll write lij dxj. Which I can rewrite as 1 over ds lij dxi dxj. And then the book makes a statement. This is equal to dij dxi dxj divided by ds, and that is justified because where d is the symmetric part of L. And this is justified because the antisymmetric part contributes nothing. See, dxi dxj is symmetric. If L is split into D and W, W is antisymmetric. So W product with dxi dxj is nothing, zero. So L, only the symmetric part of L contributes to this expression. That's why they went from L to D directly. Okay. So finally, we have finally we have ds dot. It's about time. Ds dot is equal to dij dxi dxj divided by ds. Okay. So this is essentially, I didn't want to start here and say somehow this is equal to this. I try to go through that progression. Okay. I didn't have this step already thought out. You could have guessed that because I was thinking as I was talking. What I wish you would be able to do is to grasp the basic rules clearly so that you could do this kind of reasoning as you go. What was the important reasoning we did here? It is to write dxi square root of dxi dot is 1 over square root of that multiplied by dot of that being this product. If you got that right, everything else quickly follows. Okay. So look at this derivation. We'll continue this on Thursday. Thank you. There will be a quiz on Thursday, so please be on time.